Welcome back to Air Quality Matters. We already have the tools and knowledge we need to make a difference to the quality of the air we breathe in our built environment. The conversations we have and how we share what we know is the key to our success. I'm Simon Jones, and coming up, a conversation with Paul O'Sullivan, a lecturer in Sustainable Energy Engineering at MTU, where he also co-leads the MESO Research Group. His research and professional interests include low energy demand side technologies, building retrofit strategies, indoor thermal environments, and ventilative cooling, as well as how society more generally is affected by the future of our built environment. MESO, that's MESSO, is an academic research group primarily concerned with the advancement of knowledge in the applied mechanical and energy systems research fields. This group has expertise in mechanical, thermal and energy systems modelling and simulation, specialising in areas such as marine renewable energy technology, agricultural systems and building energy technologies. I was down in Cork with Paul to talk to him particularly about thermal comfort and overheating. It has to be one of the most common questions in my field of work is the relationship of ventilation systems in overheating mitigation and control. And this subject is a fascinating element of the broader indoor environmental quality space that intersects so heavily with air quality. Our discussion flowed from thermal comfort to discomfort and ultimately overheating risk. The framing of ideas, the control strategies, and how it overlaps with many of the talking points of indoor air quality. Paul is great value, and our conversation extended well before and after this recording, full of insight and practical perspectives, a great intro into overheating and ventilation's role in it. I hope you enjoy this. Don't forget to check out the sponsors in the show notes and at airqualitymatters.net. This is a conversation with Paul O'Sullivan. The interesting thing for me with the discussion around thermal comfort and principally today overheating, which we're going to chat about, is this idea of where it fits in this broader terminology of indoor environmental quality. And as I was saying to you before we started rolling, that the air quality piece is interesting because we know it has health and well-being impacts, but often that's because of a lack of exposure to something rather than an exposure to something positive. Right, it's very little in the indoor air quality world, and probably people will correct me, that has a positive impact on your health, right? Yeah. Perhaps the microbiome, maybe, we don't know. But the thermal comfort piece, I think we all understand that thermal comfort is now part of this indoor environmental quality piece. And we don't view that through the same lens. It's seen as a measure to get a nuisance challenge,
a risk,
a performance challenge, perhaps. To work at your optimum performance. It's seen as a complex issue because people have different tolerances of it. Social science comes into play, whether you've got agency over that. Yeah. It's a little bit like acoustics for me in some ways.
It is actually, and acoustics is a good lead-in as well. To if you drop thermal, you've comfort. Yeah. So for comfort, you're dealing with acoustic comfort, visual comfort, thermal comfort. There's a broad sort of, let's say, spectrum there that you're trying to work with to achieve a sense of satisfaction with the environment you're occupying as a person. And we're talking largely in the context of buildings. So you're right. I mean, comfort, sometimes I say to myself, I ask the question, is comfort a luxury? I mean, is all our research trying to achieve something that in some ways could be perceived as a luxury, or if you even think of Maslow's hierarchy of needs, like where would comfort be on that? If you think about the need to sleep and the need to to eat and these sort of things and shelter and so on. Once you get shelter, maybe then you're saying, well, now we want to improve the quality of that shelter, so we improve our own overall experience of the buildings that we're in. Because, I think most people in the field would know we spend about 80%, maybe more, of our time inside in buildings nowadays. So the indoor environment is very important to us as much as the outdoor environment is. And that should not be a negative. Yeah. It shouldn't be a net negative to be occupying buildings that are uncomfortable.
And I suppose with this comfort thing, and I like this Maslow's hierarchy of needs thing, because it elevates a space from being a space that provides you shelter from the outside weather to something that has a purpose. And most spaces have a purpose, whether it's good sleep or whether it's for concentration in a working environment, whether it's being able to physically work, do active physical work and labour in a certain, most spaces are designed for you to have the optimum something.
Yeah, absolutely.
Right?
This idea of fit for purpose, and a big challenge we have now is we have this sort of, to some extent, you could argue there are conflicting criteria or aspirations. Like there's a need to decarbonize our buildings. And the best way to go towards that is obviously use renewable energy as a source to supply what needs you have, but dealing with the demand in the first instance. So reducing the need for energy in the first instance. And in a way to deal with that, you end up then sort of making decisions that could be seen as counter to achieving comfort, because a controlled environment, we can achieve a controlled environment, and we can do that very well. And we've seen with technology and where we are in our science and so on today, we can create comfortable environments. The challenge is to do that in a way that's carbon neutral. And buildings, certain types of buildings are passively cooling buildings, or using the local microclimate, getting free energy, whether it's for cooling or for heating, from the outdoor ambient and so on. They're ways that we've seen are very good for reducing our energy footprint, we'll call it. But what happens there then is we don't have the opportunity to mechanically intervene. Yeah. So you end up with this thing, it needs to be fit for purpose, but it also needs to be carbon neutral and resource efficient. So you're always just trying to reconcile those and say, we want it to be as comfortable as possible for as long as possible, but also in a way that's energy efficient. And that's where comfort becomes a challenge then.
Yeah, and I can't remember if we spoke about this, but I certainly had a conversation with Chandra Sarkar from Singapore about this idea that actually, when we over-engineer spaces, we narrow the scope of expectation of those spaces, and people become uncomfortable more easily.
Which is again a bit
counterintuitive. That actually we're at our happiest when we feel like we have to intervene to some degree. We have agency or in control of the space in some way, and super automated, finely controlled spaces where you see it in a lot of the standards, don't you have to be within a degree of tolerance of this, that and the other. And you're going, actually, people aren't coming out the other side of that necessarily feeling any better.
I mean, it calls to mind the axiom for me, expectation is the birthplace of disappointment. So if you think about thermal expectation, right, and you're in a controlled environment and you're aware that this environment is, over-engineered, and maybe you don't use that term as a non-expert, just as an occupant, it's a sophisticated building, we can, it's very comfortable, we can control it quite well. Any research has shown, and in practice as well, that any deviation, typically in buildings that are closely controlled or have mechanical air conditioning or whatever engineering solution, that if they can control the environment very well, small deviations lead to big disappointment.
Yeah.
That people become more sensitive to those changes, that they're less willing to adapt.
And that's why I quite like this idea of these curated spaces where you can identify and curate an environment where people can find their comfort space in a building, whether that's the lighting or the acoustics or the thermal comfort, that there are different spaces that offer up a different environments that it might be late in the evening on a cold winter's night. You might want a snug, warm or warmly lit space to do your work
in that particular moment.
But in a day, in a meeting, when you're brainstorming and everybody's on fire, you want a coldly lit space. You want it breezy and fresh airy, and you want to feel invigorated.
We're very demanding.
We're very demanding, but it's not beyond our means if it's done from the ground up to curate these environments, to create these spaces. Labeling them is a different question.
It is, and it's coming back to the idea of I think expectation, adaptation. The more aware you are, the more aware that you are of the of the limitations maybe of the building that you're in, the more you can work with that building and have a little bit of sympathy towards it almost to some extent. Yeah. And you're right, we have different needs at different moments in time and in different types of spaces, whether we're up and moving around in a kitchen, whether we're in a bedroom sleeping, whether we're in an office, wherever you are, you do have a slightly different need in terms of your comfort expectation in those places. And the challenge for engineers and architects is, how do we deliver buildings that are fit for purpose, but are also sustainable? And that's because largely a big area is, and it's been around for many, many years, natural ventilation, or using, the untreated outdoor air as a source of both primarily ventilation for hygienic needs in the first instance. But then above that, you have the need that you can say, well, we can actually use this to cool a space, maybe to heat a space to some extent, although less so. And by doing that, you can, you're doing it in a sustainable way, but you don't have as much control over it. You're relying very much on whatever you have in the moment. So then the challenge for architects and engineers, how do we design facades, indoor spaces, buildings and so on? How do we design them to maximize their ability to have a certain robustness, or even resilience is a big thing we're looking at nowadays, that they're resilient to the changing environments and they can adapt, and stay within a range. And for buildings that don't have mechanical means of cooling, there's a lot of work has been done around this idea of an adaptive approach to comfort, that we do adapt. And it's kind of linked to the thermal history of our bodies over time, the previous week maybe, or the previous 24 hours and so on.
There's that famous picture, isn't there, of people sat outside a Parisian cafe, and it's going into winter and they've all got coats on. And then there's another picture in spring, exactly the same environmental conditions to the decimal point of temperature and humidity, and they're all sat there with jumpers on because of adaptive comfort. You come out of a period of cold, it feels warmer. You're going into a period of cold, it feels colder.
Exactly. And giving people the opportunity to adapt, basically saying, look, comfort happens at the occupant level, it happens at the human level. It doesn't happen at the building level. You experience it in a short time scale and spatially very close to your own personal experience, we'll say. And on that basis, if we can't adapt, then you're not going to be able to manage your own comfort. So there was, for many, many years, the business world or the working world, there was a sort of an approved attire, you could say, suit, shirt, pants for men. For women, they would have their own, let's say, etiquette, you could call it, right? But that etiquette didn't respect the need, that there was a need to adapt. And that's changed hugely nowadays. I mean, many people are coming to work and adapting their clothing to suit their comfort needs, because Fanger did a huge amount of work back in the 70s, I think it was, and he was one of the first people to try and, I suppose, present a formal scientific language or create a discipline around comfort and say, let's study this. What are the factors that contribute to comfort, and how can we then use those factors to achieve comfortable environments in buildings? So that's where he kind of, through chamber experiments and so on, came up with the idea that, clothing has a contribution to make here, your metabolic rate has a contribution to make here, the objective physical environment has a contribution, whether it's in surface temperatures in the building, air temperature, the speed of the air that's passing.
Evaporative cooling. That was a big thing with conversation with Chandra in tropical climates, is actually getting a bit of air velocity in space can make a huge difference.
You extend the range of acceptable conditions by doing that. Little hacks, you could call them, So I suppose that's really, it's that idea of saying, well, in some buildings, you may choose the air conditioning for a particular reason. And their comfort is still paramount, but you have more redundancy and more capacity and more ability to absorb heat as it's generated and absorb external perturbations or, external influences. Whereas in naturally ventilated spaces are passively cooled, and there's a whole ongoing debate about the correct terminology around these things, but in those spaces, they're free-floating environments. So you have to, it's trickier as engineers and designers and architects to design buildings that are responsive to the microclimate. They can adapt well to changes and so on. And we've been doing a bit of work on something we call the cooling ladder. It's like a design ethos. You have the approach for a designer in this ladder, a kind of a cascading effect, is you start first with sort of preventative measures. So that's the first sort of line of defense, is you try to prevent heat coming in the first place, or the incident of heat, through different measures, and we can talk about those. And then after preventative measures, the next thing would be to look at modulating measures. So now you do have some heat in your building. How can you design the building to modulate that heat? And then finally, when you've dealt with those, you have dissipation measures. So that would be your ventilative cooling. That would be using ventilation to remove the heat, so to dissipate it. And then once you've done all those and you still have a cooling problem, you're into supplementary cooling and you're into mechanical cooling. So this kind of cascading ladder, something we've been doing a bit of work on in a more qualitative way, kind of a design ethos, a kind of a principle of how you would approach design. And we're talking about cooling because when I think of comfort, you obviously have the heating season and the cooling season. Certainly in Ireland, where we do a lot of our work, it's a cool climate. We're pretty good at heating season. We're able to decarbonize our heating systems. We're able to design them reasonably well. I think we've more challenges around cooling.
Where's the science on thermal comfort? Like if you were trying to describe to people how full the science is or complete the science is, and I understand science is never complete, but you do get the sense in certain disciplines that it's much further down the road than others. So, and we've been at thermal comfort for many, many decades at this stage. And we've been able to measure it relatively easily as well. It's been one of those things that we've been pretty good at measuring. Whereas air quality is fairly new because we haven't had the tools often to
measure these contaminants and pollutants.
So you kind of get this sense that we should have had this figured out ages ago. But I do get the sense every time you talk to people like yourself that there's loads going on in this sector, particularly in the subtlety of the science, the impact on long-term health and well-being, the impact on performance, the impact on decarbonisation. There's a lot of subtlety and nuance in managing spaces from a thermal perspective that we're still fighting. And I guess things move on as well. Like you've got the move towards sustainability and decarbonisation. It was fine, when we were just chucking energy at air conditioning a space.
Yeah, right? and before the Arab oil crisis in the 70s, there was never a problem discussed around energy in general, but also energy in buildings and air conditioning as an energy intensive sort of service that we have in buildings. Like I wrote down POE when you were talking there, post-occupancy evaluation, and because where are we with the comfort science? I think there's still a gap between research and practice. So there's the science is established, but there are an infinite number of buildings in the world, and it's very difficult for all those buildings to get access to all the right research and to be monitored in a way that comfort can be achieved successfully. So I think the science is established, and there's still loads of debate, like any field, whether it's adaptive approaches or static approaches, which are the best approach. What different factors contribute. There's some research that says that we should be exposed to extreme heat and extreme cold. That variety or variability in your thermal exposure can be good for your health and your kind of, your resilience and so on. So I mean, I think the science, we can talk about, there's lots of, good science, but I do think there's still this gap or this challenge where we build buildings and they don't have research teams behind them. They're engineered well and they're built well, but that's a very complicated process with lots of stakeholders. Then the building is built and it's occupied, and very often the experts who understand that building drift away, or they don't have any obligation to see out the calibration or fine-tuning phase. And I think that's a problem, is taking buildings like the one we're in, which is a brand new building, and ensuring that we deliver on the comfort by staying with the building long after we've built that building, having a relationship as engineers and designers and so on.
Is there, I was just writing down there, operational performance, is there this performance gap challenge, the same as we have with almost everything else in indoor environments? Like theoretically, we know what we should be able to achieve, and obviously we're still refining that. But when we go out to actually measure the performance of the real spaces, because the built environment, as you say, is an incredibly complex place with many age groups, lots of buildings run to failure, lots of stuff that there's different tenures and ownership models. There's lots of places for this to fall down. So people's lived experience of thermal comfort in buildings is probably very different to on paper theory.
And there's a lot of good work being done. I mean, and again, I can speak to Ireland probably more than other countries because that's where I exist and work. And, SCAI as a sort of a government agency charged with dealing with our energy crisis, they're doing a lot of good work in supporting research, looking at comfort, looking at indoor environments, looking at the role of ventilation, the role of, and their work in particular is looking at field measurements. They want data on real buildings. They don't want as much theoretical studies when it comes to buildings. Let's build up our database. Let's build up our knowledge on how are real buildings actually operating. And so that's a big area. We were in a room here. This is a brand new building we're in today for the podcast. And we were in a room meeting last Friday, myself and some colleagues, all building professionals. And the room was very uncomfortable. It was a meeting for them. We couldn't solve that problem. There was no openable windows in the room. There was a radiant heating system. There was a ventilation system. And there was just this kind of weird interplay going on that the room was warmer than we would have wanted it to be. And it was a sort of an example of where, these buildings are very complex and they need to be lived in and tinkered with to get them to work right. It's like a car. It's like, you want to keep that engine ticking over. You want to get it maintained well. And you want to get some feedback of what's happening in that when something goes wrong and correct that. And I think that's a challenge still for us. So the science there's lots of really good science, but we still have a bit of a gap, I think, or just sort of a disconnect between research and industry.
And with the advancement in technology, there's also this assumption that buildings are going to take care of us. And in many spaces, there's still an art form required to get the most out of those buildings.
Absolutely,
you still need maintenance people and operational people and people that know how to get the best out of a space. It isn't all digitized, and there isn't somebody that can just pull out an app and go, well, I'm going to change it by half a degree. Like that experience that you found, a room full of engineers and not one of them able to have any
intervention or agency
over that space. And that, nothing makes you feel more unsatisfied than no agency.
Yeah.
Right? Because the moment it's bothering you, it's like that annoying HVAC system sound or the flickering light. The moment you can't do anything about it,
you feel a bit helpless. And it has your frustration in another way, and you're not as productive in your meeting. You're distracted by it and so on. And there is obviously systems now that we can intervene with and so on. Like a lot of work has shown that the more control you give to an occupant, and this doesn't sound too scientific, even though there's a lot of science behind it, that the capacity to open a window actually is hugely empowering for people to, achieve some sense of comfort at no energy or carbon cost, So openable windows, and then there's a little bit of science in that as well. And that's only one area, like, blinds, open windows, the capacity to adapt your clothing, to be able to open doors and to have a much more of a fluid approach to your working spaces and your living spaces. That significantly contributes, or significantly, let's say, helps us, or avoids us going down the road of retrofitting air conditioning systems or energy intensive systems on. So there's a big psychological factors we talked about earlier today. But I think it's not all about sophisticated mechanical or engineering solutions. That actually a lot of the solutions in comfort are psychological or just more natural. The interventions, like I said, an openable window, the capacity to change into a jumper or a jacket, like they're big things. And there's a lot of research needed to kind of convince corporations, businesses, organizations of that as well. If you have a call center with 800 people in a room, you're going to want them to be productive. Yeah. So it's a hard choice to try and convince someone that you should do that, without the capacity to control the environment within half a degree.
We've kind of been dancing around this thermal comfort, discomfort problem, but the reason I wanted to talk to you specifically was about when it becomes a problem, and we start talking about this word overheating.
Yeah.
Is there a definition for what overheating is? Is it easy to articulate to people what we mean by overheating?
We're working on a piece of work at the moment. We're evaluating over 20 different indices that all claim to be able to characterize overheating. So there's a lot of debate and a lot of different ways you can approach that, like in terms of if you think about overheating, obviously at the You can talk to a non-expert, a family member this evening at home. They'll know if they're hot or cold. They'll know if they are too warm. So if you have an environment that leads to a thermal sensation that can be characterized as too warm, or you're outside, we'll say, an acceptable thermal sensation, or that you're thermally neutral, right? You're either, you're in an overheating situation because the person themselves is saying, I'm too warm in this particular situation. The problem is that that's very subjective. So you have to find an objective way of coming up with some criteria to say, when can we say a building is overheating and when can we say it's not? So we need some criteria to do that.
Where's the line from uncomfortable to overheating? And can the two coexist? Can you be uncomfortable in a non-overheating, and can you be comfortable in an overheating?
Well, again, Fanger would have developed what we know as the PMV model. The PMV model is a scale. It's a 7-point scale from minus. They vary, but we'll say -3 to +3, where 0 will be what you're trying to achieve. That's the perfect thermally neutral state, that you're neither cold nor hot, that you're able to focus on what you're dealing with and you're not distracted by that. And so that was the starting point. That's still used today, that scale. A lot of research work would go into real buildings and we would do surveys and we would so to understand whether a particular design solution works well or not, and maybe generalize some of the findings, if it does work well, to share that knowledge with other people so they can adopt those solutions, you would typically do thermal comfort studies. And those studies would involve setting up an apparatus that would monitor air speeds, mean radiant surface temperature, air temperatures. You would then record the clothing levels of the occupants through survey, their height, age, gender, deduce their metabolic rate from that. So what I'm trying to get with that is you can then, by surveying those people under different scenarios, they can mark on their 7-point scale how they feel in those moments. And then you can say, okay, when we had these conditions, people were happy or comfortable. When we had these conditions, they were a bit too warm or a bit too cold. So it's through a huge amount of work over many years with that surveying type approach that we've been able to come up with models and, objective prediction approach that says, okay, based on a large enough sample size, we know that when we see these conditions, typically people will be uncomfortable, or a certain percentage of them. And that scale gets mapped to a kind of a distribution that says, when you're 0, you get about 80 to 90% satisfaction. It's very hard to quite get the full 100. And when you're at -3 or +3, you're down at about 10% satisfaction,
And from an engineering perspective, does it ultimately boil down to a classification that where a building's systems, whatever they are, aren't able to keep that building within design temperature, that building is in a state of overheating? I was in the Middle East in August this year, right, where average outdoor temperatures were nearly reaching 50 degrees, right? And the buildings I was in weren't overheating. Even though the climate was extreme, that building was not in a state of overheating because I'm assuming the engineering controls were able to keep that risk at a tolerable level at a design temperature. But buildings in the tropics that are much more open to the environment, when they're at 35 degrees and 90% humidity in monsoon season, we're not classing them as overheating. There must be like an engineering state, but outside of the comfort piece where this becomes a health problem for vulnerable people and so on, I'm guessing there's a point from a technical specification.
There is, So, and if you think about it, overheating largely only applies to buildings that can't control their internal environment. Because a building so if you're in the Middle East, you think about any space that you occupy, the temperature in that space is a product of the energy balance in that space. The net amount of heat gain into the space and the net amount of heat out of that space. So that energy balance will lead to some temperature. Where you have a mechanical system to cool that building, that contributes to the energy balance. We say we want this building to be 21, so at whatever energy cost. So you can actually have a system that will add or remove heat from that space to keep it cool. So that will almost never overheat. So overheating as a criteria doesn't often apply directly to mechanically controlled spaces unless you have a failure with the system, and
so conditioned spaces
typically don't suffer
as long as you've engineered those conditioning systems correctly. They've got the right evaporative cooling sizes. They've got they've got enough energy to put towards them. In theory, if you design them correctly, that they'll only overheat if they're
in a failure mode,
or if in an extreme weather event.
And that's this idea of resilience. And we might circle back to this in a while.
And come back to power outages and things like that.
Resilient cooling and work that was done recently by Annex 80 as part of the IEA EBC program. But so it's under normal operation. Overheating is typically a criteria we use to evaluate whether a building is fit for purpose when it's free floating, we call it, when there's no capacity to regulate the indoor temperature during cooling season. And a lot of buildings will be like that. And most homes in Ireland are like that they can control the temperature in the building to a point, at which beyond, when you leave the heating season, you no longer have much control over that outside of whatever cooling potential is available in the outdoor air. So overheating is really, it's a criteria or it's a phenomenon linked to buildings that don't have cooling systems. So
it's quite a good way of compartmentalizing this. So for conditioned spaces, so in parts of the world where they have been engineering spaces to be conditioned for a while, this is an engineering problem to solve, right? This is adding more.
It's a comfort problem. And they'll deal with, like, you'll still have draft issues, you'll have overcooling issues, you'll have overheating issues, but in a different way, not as the building's response to its environment, external environment. They might be, as you say, a poorly managed system, inside the building.
And actually, funnily enough, in the really hot spaces, the thing that I was really struggling to wrap my head around was this overcooling scenario that goes on, where when you're particularly hot and humid climates, where you put a lot of energy into getting the moisture out of the air, so you overcool the air, but you then have to apply energy back to bring the heat back up to a comfort point. And there are regulations like in Singapore where you're not allowed to do that. It's an energy penalty.
And we do that here. I mean, even in Ireland, particularly in close control spaces like clean rooms and so on, they would use a lot of systems like that. And research shows that beyond about 12 degrees, I think, 12, maybe 13 degrees, below 12 or 13 degrees, we become perceptually aware of that as a thermal discomfort or a draft effect. So if you want to bring air into a room, you should try and have it, around. Some of our research looked at that as well for naturally ventilated. So when you open a window, at what point was the air becoming too cold? Because there's huge cooling potential in the outdoor air. And I'm probably drifting a bit, but if you think about the way we're building our buildings nowadays, they're very airtight, they're really well insulated, particularly in cold climates or cooler climates. Our big policy drive has been to decarbonize for our heating seasons. And that's easy, that's done through, heating buildings sustainably, but being able to keep that heat well controlled and inside the building. The unintended consequence of that is that those very same buildings can't get rid of the heat easily in the summertime. And what we're finding is in Ireland, our cooling season was from May to September-ish. Now it's March to October. That in highly let's say NZEBs, or buildings that are now built to the A1 kind of standard regulations, we're certainly finding that these buildings need cooling in March. And the great thing about Ireland is it's available. We don't need air conditioning. It's there. You open the window. It's why data centers, I think, Ireland's attractive for data centers, because there's a huge free cooling potential for data centers for large parts of the year as well. When we have good diurnal swing and we have low temperatures. So
I think this is a really good point to kind of set the context, because what we're predominantly talking about in reference to our conversation are buildings like homes that are unconditioned, so they don't have air conditioning typically. We're talking about often naturally ventilated spaces or mechanically ventilated spaces without air conditioning elements to them. And the challenge we're finding is that we've fundamentally changed how we've built these spaces, right? We are able to have very light construction if we want it. We can have very heavy thermal mass construction if we want it, and we have the full spectrum of that in our built environment. So it's not like we have one traditional approach to construction. We've got incredibly good glazing these days. We've had our concepts of what looks well has changed.
Yeah, absolutely. Yeah.
You know, the Dermot Gavin stick a window on it approach to renovation. That's an architect for international listeners who's famous for putting big windows on everything. But, you know, we see that in apartment blocks and so on. There's a very classic design for things. Like we've created a rod for our back, haven't we, in very airtight buildings.
Like it's certainly another conflict that you have in design is the aesthetic.
Yeah.
And we're driven by a certain aesthetic, and that can then have consequences for the footprint, you know, the resource footprint of the building.
A lot of the problem, as I understand it, with overheating is not just the temperature that's possible to reach, which we've heard stories, both anecdotal and that have been researched, that have shown quite phenomenal temperatures being achieved in the wrong spaces. But also, as you say, the potential for the amount of time that spaces can spend in this overheating state. And I think everybody you don't have to be an engineer to know what an overheating space feels like. There's enough summer heat waves that we get in this part of the world, even
nowadays,
that everybody recognises that where you just can't get the temperature down even at night. That the heat is just
you can't get rid of it.
In the walls. There's no difference between inside and outside, and you might, if you're lucky, you might see half a degree or a degree of temperature change overnight. We all know that instinctive feeling, and for those of us that are well enough and that can adapt to that, that's not necessarily a problem. We might not sleep very well for a week or a few days, but there are people in society where this kills them. And this is a real issue, isn't it?
It's becoming a big issue. Yeah. I mean, one way you can look at your building, and like if we talk about buildings like in our climate, our homes where we just don't have air conditioning. And we have big pressure already on our electricity grid, it's not really an option just to do a national. And we may very well, in time to come, have the renewable energy potential available to supply electricity in a green way, but just the physical infrastructure to actually retrofit is just not going to really be practical.
Yeah, unless we want that image that we see from Asia of split
units hanging off the building. And like we want to try and step back or avoid that happening as much as we can, because again, the art has an architectural sort of sensibility in how we want our cities to look, you know. But if you think about buildings or homes as thermal batteries effectively, so you know, this idea of a building as a battery. So you know, the building is a thermal battery, depending on how heavy massed that building is. And you talk about that at night time, we've all had that experience where, you know, you just can't get rid of that heat. If we design our buildings in a clever way, that they can absorb quite a lot of heat during the day, and then they have some mechanism to cool that heat at night time somehow, or to remove that heat, you can really contribute to broadly comfortable conditions, no need to sort of resort to air conditioning interventions and so on. And it's about looking at the morphology of these buildings, looking at, you know, the architectural design, the material selection, and say, how can it becomes a very holistic, integrated process. And it doesn't sound too scientific from the outside, but there's a huge amount of science needed to get a building to respond dynamically with its own climate, to let's say, to perform well. And I'm thinking about things like white roofs, cool roofs. There's a huge amount of work being done on material choices so that we can reflect a lot of our heat through radiation to the sky vault at nighttime, so that the building can cool through a radiative interaction with the environment around it. The thermal mass is available to the air inside the building, so the heat can move into the thermal mass. The building we're in, again, it's all exposed concrete in this new building, so this building can kind of regulate and respond in a more, I like to use the analogy of the church versus the kind of tin shed.
Yeah, in a softer way.
Yes. Yeah. You've got a kind of a phase shift. So the peak solar radiation in a given day could be around noon when the sun's at its highest. But you want to try and see if you can avoid the peak radiation gain to a building coinciding with the peak outdoor ambient temperature, because then you get this double heat gain effect. So heavy mass buildings will shift because radiation has to first go into the structure because there's a surface-to-surface interaction, heat up the structure, and then it returns into the air and the building will warm up. If you can kind of create a phase shift or a delay between the peak air temperature in the daytime and peak radiation, you can sort of dampen that that sort of.
And I think you don't have to be an engineer again to have a perception of what this looked like. Anybody that's been to the Mediterranean, to North Africa, to countless places that deal with moderate high temperatures. We see that in the vernacular of those buildings, the designs all over the place, elements of it. So I don't think it takes a big mental leap for us to picture what good might look like for our buildings.
Yeah, absolutely.
External solar shading, a good purge ventilation potential, high ceilings, passive stacks, safe spaces. We must come on to that kind of safe space, room. Even within a building, you have spaces that might react differently to others. I think we can all picture that, and particularly us living in Ireland, great, wouldn't we all love the Mediterranean a bit of the Mediterranean lifestyle in our building vernacular? But I think the challenge is that, and it's the problem of Europe and areas like that on the planet, where the building design problem is one of existing buildings. The in the next 20, 30, 40, 50 years, the vast majority of the stock that we have to manage and live and operate in already exists. Yeah. And we haven't designed those buildings typically to manage overheating. Yeah. Now, we get lucky, some buildings that have got high thermal mass, the church, people, older buildings.
At the extreme ends of that spectrum,
might actually suit, ironically.
They might work well,
overheating. But the vast majority of the buildings that have been built in the last 100 years have not been designed necessarily to handle overheating particularly well.
No.
You disagree with that, yeah?
No, I don't disagree with it, but it brings me back to this idea of the building as a sort of a living thing to some extent, right? And not to get too romantic about it, but you can design, and I come back to this cooling ladder, you can design good preventative measures, solar shading, using flora, trees and so on to act as shading devices, and also to help with sort of managing wind around buildings and so on. You can do your preventative measures, you can do your modulating measures, thermal mass, these sort of things. But the problem with those buildings then is that they require a relationship. You can't just switch off and come in and say, the system is dealing with it. The temperature will always be the same because I've actually installed a mechanical system to deal with that. So these buildings, we do know how to design them. We do know how to build them. We struggle to manage them and operate them, I think, properly, And I think if you think about this idea of vulnerability, we were touching on that earlier, where when you go outside the comfort range, which is a sort of a preference, satisfaction, well-being, productivity, there's another scale above that, which are into heat stress, morbidity, mortality, extreme exposure, and that's with vulnerable groups. So if you're trying to design buildings that are sustainable and decarbonized, and you want them to be highly coupled to their outdoor environment and to work with the environment, but you also have vulnerable people inside that building, you are into a risky space there. And you have to be very careful as designers. And that's why sometimes we do resort to energy intensive solutions, because there's an overriding need beyond the decarbonizing need is like, well, health and life, we'll say, in the first instance is more important or critical. But it's just that continuous dialogue we have as building professionals or building designers is, how do we design these buildings that can work well and they can give us healthy environments, but they do need a continuous relationship, like they need to be managed,
And is there a kind of process that's going on in parallel to the same kind of process that's happening around the energy intensity of our building stock, that we're starting to look at a national level of the building typologies and the stocks that are going to present a particular challenge over another?
Absolutely.
Because the reason I asked that question is one of the things about climate change is it's probably moving at a pace that humans can adapt at. One of the challenges in the built environment is when technology flies ahead, right? So we've seen a massive change in the need for sustainability and decarbonising the stock. That moves much faster than skills and the trickle down, the conservative nature of construction. And so we end up creating these risks, these unintended consequences. And we see that in retrofit of existing buildings, that we create risk where we didn't need it because we haven't learned fast enough for the pace of adaptation or valued the risk appropriately. But something like overheating, if a good proportion of the stock can be adapted over time with shutters and better windows and solutions that are, not and
something like phase change materials that have a high thermal capacity and that they're not really yet at that commercially. They haven't reached that saturation point where they're now normal or readily available. But things like that.
You get the feeling we've got a bit of time. Like in some of the stock, I'm guessing we've got a bit of time to sort this out. As the problem creeps, we can adapt as it creeps. But there are some spaces, like, we see certain apartment blocks and certain new builds that are already well beyond the pale when it comes to what's acceptable.
Again, and I think cool climates are of interest because it's a bit of a juxtaposition to say, how do you mean overheating in cool climates? Is that not just something in Southern Europe that we are used to experiencing? And we're saying, well, nowadays, cooling needs are no longer linked solely to the ambient, right? It's how we're designing and operating the buildings. Again, I keep coming back to that, that because we've got very efficient buildings that work well in the heating season, and it's been a great success in terms of reducing energy use, we have to find a way now to deal with those buildings when we've got accelerating ambient conditions, but also just as a building themselves, they're not good at heat escaping. And we need heat to escape sometimes of the year,
And is it hard to do this well? Because I get a sense, you look across somewhere like the UK that's started to develop Part O of the building regulations for overheating. There's a lot, you hear back through the grapevine that there's a lot of problems with that. They're struggling to implement that practically, that there's lots of weaknesses in the methodology. You come somewhere like here and we don't even have a Part O practically, right? That is there a roadmap even now, as we stand here today? Is it clearly definable and possible for architects and engineers to be creating spaces that don't overheat? I guess you'd say yes. This isn't beyond the pale of people to think about overheating potential.
What's very strange at the moment is a couple of things come to mind. One is we're in an unrelated study looking at heat pump research, or we're looking at the performance of heat pumps. In that project, we've also looked at some of the air quality conditions in buildings that have heat pumps retrofitted. So homes that have been refurbished, social housing in particular, they've had heat pumps installed, and we've been looking at the indoor environment as well as the performance of the heat pumps. And one of those we were looking at last week, we had some data coming in from a home in Cork, and you're looking at 4,000 and 5,000 ppm for extended number of hours in the building, in the home, which is basically a proxy to show us that people don't use windows, they don't open them. Months can go by without opening your window. So you're saying, yes, we can keep buildings cool, but it's about working with that building,
Yeah.
Night cooling is a huge solution to overheating risk because we have a huge potential at nighttime to dissipate heat to the surrounding urban and suburban and the sky vault and so on. But if you're a ground floor apartment, if you're a home, a detached home, you can't really open your windows at nighttime. There are burglary issues. You have inclement weather, rain issues if it's raining and so on. Other issues around high winds and noise as a result of that. So they're very subtle kind of challenges. It's a case of, if you do the right amount of night cooling, if you have the right thermal structure available to you, if you have the right amount of dynamic shading that maximizes passive gain in the winter. So you want to get that low angle sun in the winter, but in the summer you want to block that high angle sun, that you have those types of interventions, which are commonplace in other parts of Europe, but not in our cold or cooler northern climates. There's a lot of work involved in that. That's not necessarily a technology challenge. It's a perception and a socioeconomic and a psychological challenge. It's about educating people. It's about saying we need to kind of change how we live a little bit, or we may need to change how we live and be more like Southern Europe. Maybe we need siestas at some point. Who knows,
I'll get you back to the podcast in just a moment. I'd just like to take a minute to tell you about Zehnder, one of our partners. Zehnder is one of those companies that, if you're working in indoor air, you've probably come across. They really cover the full spectrum when it comes to ventilation, from simple mechanical extract right through to full climate systems where fresh air is enriched with heating and cooling. They offer the ventilation units, and they also offer everything around it: air distribution components, smart controls, the expert advice to make sure systems actually work as designed. One of the things I really like about Zehnder is their focus on knowledge through their experience centres and the Zehnder Academy. They help professionals keep pace with this fast-changing world of indoor climate. Whether it's tackling overheating, improving indoor air in tight retrofits, or simply making sure your filters are doing their job, Zehnder brings experience, depth of knowledge, and clarity to the conversation around healthy buildings. So if you're involved in building design, housing, or indoor environmental quality, they're really worth checking out. Details are in the links in the show notes at airqualitymatters.net, of course, and at Zehnder, that's ZEHNDER group.com. Now, back to the podcast. We've got a demand for housing, and we really need to scale housing, and we've got the ability to do off-site construction and modern methods of construction, and we feel like there's a need for these silver bullets, these kind of one house fit for all purposes. You realise when you get, this conversation just highlights to me, because it's the same one you have in parallel when it comes to acoustics and particularly air quality, that spaces are complex spaces and you need the time and resources and funds to design these spaces, not necessarily individually, but cognizant of that building's particular need. Because just a slight change in orientation could flip a building.
Yeah, absolutely.
Or even if it isn't the solar gain element, it's the fact that you might have purge ventilation capability through louvered shutters on the windows, but if your building is particularly exposed, that ain't going to work for you.
Exactly.
In Ireland, because we know. I mean, I live on top of a hill here in Ireland, and you virtually don't need penetrations in the fabric of our building for 75% of the year. The air finds its way in. This is a modern home that I built relatively airtight. So a kind of a big purge shuttered kind of louvered window approach there, you might struggle with.
It's actually interesting. You mentioned that. It's slightly unrelated anecdote, but Ciara Hearn at TU Dublin is doing great work in overheating with her colleague Mark Mulvihill and others. But some other work that she's done and she's spoken to is that they've seen that the oil consumption in schools is now more correlated to the wind speed than the air temperature, because the buildings are well insulated, so the air temperature is not really a big driver for the need for oil. It's actually the wind speed and the wind direction.
Shout out to Jeff Colley. Actually, I remember having conversations with him back a decade ago, I think, where we'd been through a couple of particularly windy winters, and he started looking at the data from a wind speed perspective rather than just a temperature perspective. And we found that
there's correlation,
discomfort and energy use, particularly in Ireland, because for listeners, we have a winter when it's at its worst, where you have sub 7 degree temperatures, very high humidity and high wind loads on buildings, which is a really horrible energy mix. It's not a cold, dry, still climate.
It's always a challenge for Ireland. It's a real challenge for designers as well to try and address that. Kind of very humid, but and as you say, moist. Cold but moist, as opposed to that dry, cold weather.
Yeah, particularly hard on heat pumps. I mean, we know we've been talking about heat pumps, but heat pumps really struggle.
The de-icing problems.
That zone between kind of 3 and 7 degrees, like high humidity, can be a challenge. If you've been used to designing heat pumps for cold climates, it's a different kettle of fish.
Another thing, actually, that I just, you reminded me, we can design buildings well and so on, and we're thinking about those challenges. Something that we've noticed, which we find a little bit interesting, is that we're just finishing off or concluding a project now. It was called Resilience, and we looked at 30 non-residential buildings in Ireland. We monitored their conditions over, I think, about 300 different spaces across those 30 buildings. And again, the question was, do high-performance buildings that are, high-performance non-residential buildings overheat? And if they do, why do they do that? We found that the simulated work we did on that So Met Air have released the Translate data set, I think it's called, which is future weather files. Our simulations are actually showing a fairly robust building stock into the future. That NZEBs. We looked at a school and an office in particular in that situation. We did some analysis of those, and we published work on this office, and we're soon to publish work on the school. They're broadly robust, that they're broadly able to withstand ambient warming in the future and maintain comfortable conditions for a sufficient amount of time of the year. Not all year round, but within the criteria, and we can maybe circle back on criteria at some point. But we found that, so the simulations are suggesting that there is some overheating, but it's by no means as bad as the measurements we found.
Let's look at that for a second, because that's interesting to me. Because on one hand, we're saying we've kind of moved our buildings to be significantly more airtight than we used to build them. We've improved the insulation levels typically, and it's created this environment where we're not able to get rid of heat once it's there. Right? Once we go past a certain point.
Without night cooling, because we actually have a really good diurnal variability in Ireland, and UK and these. So actually, if we can, night cooling is really, really powerful as a tool. It's just not really. There's what's the term I'm looking for? There's a cultural sort of barrier a little bit with that, because again, it involves a little bit of automation, maybe. It involves.
Well, we should come to that at some point, because I know, particularly with the NZEB homes where you're starting to, or nearly zero energy homes, where you've now got a lot more heat recovery units. The advantage of that in winter is obviously you're recovering heat, but if you don't have well controlled summer cooling on those devices, you're not dissipating the heat in the same way you were doing with non-heat recovery devices. But heat recovery devices that have got summer bypasses, they are able to bring, they can make a huge difference. Particularly, like you say, with the Irish diurnal temperature profile,
those systems can be run at night time. Absolutely. I think we at some point get to this new technical specification we've been working on in Europe around designing ventilative cooling to try and increase information available to designers to help them design for cooling in these kind of climates. But you're right, within that language, it kind of came out of Annex 62, which we worked on a number of years ago, that whether you supply air naturally or mechanically, both can be seen to be passive, we'll say, for want of a better word, as long as there's no mechanical refrigerant involved in cooling the air. So if you don't treat the air and you bring it in and you just access the cooling potential, you're right, many homes in Ireland in summertime could and should be running their MVHRs if they have a summer bypass.
Let's put a pin in that and come back to it, because I think that's something we'll spend a bit of time on, because it sits really nicely with the air quality of this podcast. But just back to this modern buildings, I thought it was interesting that we've kind of moved our buildings into a place where we are creating a bit of a problem for ourselves, but yet also when you look at those modern high performance buildings, they also offer some resilience there. And I'm guessing that comes from the fact that they can be thermally insulated from the outdoor environment. So there's a benefit of good insulation. There's a benefit of good air tightness, that heat isn't leaking in. You're in control of that space.
There are some,
So the things that can cause a problem can also shield you from, particularly, I guess, those peak daytime temperatures. Like if you can manage radiant heating and solar gain properly, you can protect yourself from physical heat outside.
I mean, if you can get access to the cooling when it's available overnight, early in the morning, we'll say, and then you shut down your windows, you don't open them throughout the day. So think about it, if you can get the cooled in, or the access that cooling, get it in when it's available. And then think about it, you shut down your blinds, your shutters, you just go into bunker mode, we'll say, for periods of the day. You have a safe space there.
And I think people get that. Anybody that's been on holiday in Spain, right, knows the power of external shutters that allow air in but stop the sun coming in, where the shutters come up one side of the building in the morning and down the other side. You're playing with the space to protect yourself in that environment.
And they're behavioural challenges that we just need to adapt a little bit more in our summers.
But we don't have that technology either here. It's very rare that you'll see external shading. Well, you're starting to see some external shading, some ideas around overhangs and tree planting and so on. But we're a little way off external shutters here. still, I think.
Yeah, and certainly in the residential sector, in the non-residential, you will see, and for many years we've seen really well-designed buildings with external sort of solutions to avoid, solar gain and so on.
But I'm assuming even in internal shutters or internal blinds, if they're reflective and they're bouncy, you're not getting direct radiative heating of surfaces through the glass. You can keep that. I mean, it's not as good as an.
It's not as good because that radiation just converts to conduction. And
But it will limit.
It will limit it. Yeah. I mean, it's just that was the point there, is that if you can get a building cool, you can keep it cool if it's well insulated, as long as the source of heat gain isn't internally. So you might come to work in an office and maybe that office had some night cooling and it has a nice thermal structure, and we're back to the building as a battery, that you're not cooling down the air mass, you're trying to cool down the structure. So that can absorb much more heat throughout the day. So you without night cooling or without the thermal mass availability, these things it's just not going to work, So it's just, and a lot of engineers know this, a lot of architects will be listening to this podcast saying, yeah, we know this, we're long in the tooth now. The challenge, I think, is implementing it, and the challenge is a few things. One is published, demonstrated, exemplar case studies to prove to developers and clients, look, this can work if it's managed well and properly. So I know, have a lack of data from buildings that work well, and that's published, that people can look and learn about those buildings and say, take that back to their own design office and say, this works well if we tweak this and tweak that. So evidence is a bit of a challenge, because you have to go out to buildings, seek consent to those building owners to get in and set up all your tricks and, your box of tricks and so on, and whatever you have, and then leave them there for a while, monitor, come back, hope that the data didn't drop because of some problem with the Wi-Fi. There's a huge practical challenge to getting data from real buildings and looking at that data to say, does it work well when we were operating in this mode or that mode, and what solution is the right solution for those particular situations? So that's a huge challenge, and that was that project that we've done that now for 30 buildings in Ireland. The measurements have shown us that there is a big overheating problem in our commercial buildings. The simulations are suggesting there's not. So there's a really interesting narrative there, that why are the simulations not showing us what we're seeing in 2023 and 2024 in terms of elevated temperatures, but the severity and the duration of those, we're not quite seeing it in our simulation work. And these are calibrated models like that. We've auto-tuned them, or we've tuned them with real data so that they are predicting reasonably well. And I think a lot of it is the weather files. Again, they're not moving fast enough with the rate of ambient warming that's happening. So we produce future weather files, and then within a few years, they're almost redundant.
Yeah, and I think it's important to set the context here a little bit as well. There are buildings, and my building is a prime example of that, where the house that I live in, where there are going to be periods of time in summer heat waves where that building is going to overheat a bit, right? And thankfully, we're in a healthy position where it's not going to be a problem to us. So we're not really talking about that kind of a problem, but there is a swathe of people living in buildings or working in buildings where the amount of time they spend in a space that is overheating, in whatever measure you want to practice, is a problem, is a really significant problem.
We've seen it in Europe with the deaths around the heat waves and so on.
Yeah, totally. Yeah, and like you say, the elongation of the heating season, of the cooling season as well. I think perhaps the interesting thing here is there's also a bit of catch up on the demands and expectations of the consumer here as well. Consumers in cold climates, I think, have got to a point where they rightly expect a building to be thermally comfortable in the heating season. And if you are selling an A-rated home from any of the major developers, and people are moving into those properties and they are cold and drafty, even if when they're practically heating those spaces, fuel poverty aside, then there's a demand and an expectation that I haven't got what I paid for here, right? And you see that, particularly voracious WhatsApp groups popping up on developments where there might be poorly installed windows or something's happening where people are not satisfied with the level of product that they've bought, because we've set an expectation that you shouldn't be spending 300,000 or whatever it is in a property. I'm probably massively undervaluing it. That's the entry point now for homes. Right? Yeah. 500,000, whatever. The expectation is, if I'm spending that kind of money, I am not prepared to be sat in a living room in November with a light jumper on, feeling chilly. That's a reasonable expectation. Yet, we've probably not played catch up yet, where enough of society is going, hang on a minute, I've bought a home, I've bought a product where for an unacceptable amount of time during the summertime, this building is not comfortable. There are rooms that I can't go in for large parts of a day because it's overheating. And sometimes that's on us. Like as the public, we need to set our levels of what fair is, what our expectations are. It's a human right to be able to be in a space and it not to cause you harm. And there are whole groups of people, particularly in apartment blocks throughout this part of the world, that can't access parts of their building for large swathes of the summer because of the heat. That's not right.
It's not right. Yeah, and it's back to that fit for purpose statement again. You know, we seem. The thing about buildings is they're not manufactured they're not built on a production line in a factory run by a particular brand that has a proven track record, let's say, of delivering, and they can be held accountable as a brand in a general way. They're still very much bespoke, one-off approaches. We haven't quite achieved that repeatability in the rollout of how we build our buildings. So there's always challenges in build quality, build practices, cultures around that sort of thing. We buy a car, we have a huge expectation on its miles per gallon, its efficiency, its comfort.
And there's countless websites you can go on to compare them against that brand and another.
It's very hard to compare homes, and as you say, it's more of a citizen ground up thing where you WhatsApp groups and.
Do you think that's going to change? I mean, I use this car analogy the whole time with air quality because the feedback loops with cars, the data that's available, the sensors, for the cost of that asset, the information feedback loops from is huge. But in the built environment, we don't have that.
There's many people right now with infants in brand new homes as young couples, and I've had some speak to me, directly about this, that they're extremely worried about the welfare of their child for 2-3 months of the summer, because any bit of heat at all, they're saying we can't cool down the house. We don't know how to do, and again, we can't leave the window open overnight, or maybe we can, or we're a bit worried about that. And it sounds like such a basic thing, but yet it's just trying to come up with a solution that works can be a bit of a challenge.
Do you know if there's any evidence to long-term chronic exposure to overheating? With the same as with air quality, we now know that long-term exposure to certain stressors, whether they're direct pollutants or whatever it is, that there are impacts. We know that with noise. Like if you're creating stress, chronic stress on the body from all sorts of different reasons, this has long-term health impacts. So is there evidence developing here?
There is. That has been around for a while, that long-term exposure to elevated heat can have unintended or negative consequences. Funny enough, again, coming back to it recently, there was work done by, I think it was Hannah Palubinski and colleagues, where short-term exposure to extreme temperatures can actually be good for you in terms of your resilience and your robustness and your kind of, I'm trying to think of the anecdote of going out and playing in the dirt, the mother saying that's good for you, like it builds your tolerance and it builds your kind of, but Shane Coakley actually in I think it was at UCD when he did the work, maybe it was Ulster, University of Ulster, but he published a paper recently with 50 homes in Ireland, 37 of them were passive houses, and 48% of those homes, it was data from a collection of homes, 48% of them had failed criterion for overheating. There'd be different criteria, so SIBC would have TM59, and you have some criteria looks at the severity of overheating, some looks at the duration. So there is evidence that certainly homes are overheating. They are uncomfortable, and again, comfort for me sometimes is a misleading term, because it's saying, well, what's wrong with a bit of discomfort? But there's big problems for the elderly, big problems for neurodivergent people who actually just don't have the capacity to understand how to interact with their home. and big challenges for infants and those that actually, you know.
But increasingly, we're appreciating the value of sleep, for example, on long-term health and well-being. If you're in environments where you can't get comfortable night's sleep, and temperatures are one of the key factors
It
for
is,
good
usually
sleep. Like this will have impacts on people's long-term health and well-being.
And bedrooms are a big problem. Kevin Lomas in the UK has done some good work on bedrooms, and again, lots of published work there showing that, you know, there's huge evidence of unacceptably high temperatures now in bedrooms in the south of England and so on. And tackling that is a challenge without resorting to air conditioning, you know.
It sounds like, I mean, because I kind of asked you the question at the beginning, it feels like thermal comfort and temperatures in buildings should be something we should have a good handle on by now. But it seems like there's a lot of work to be done, and particularly as the climate changes and our building technologies change, and like there's a lot of good work to be done here, isn't there?
It's a tricky one. I mean, I'm like yourself, sometimes I'm thinking, you know, we kind of have it on paper. We know what level of intervention is needed. And it's not a case of, so a big thing that we would look at under this idea of resilient cooling solutions is that really it's hybrid solutions is what we need. It's not all air conditioning and it's not all passive.
Yeah, and I was going to ask you about that, and it's a great segue onto the ventilation part of this, is that, you know, as a ventilation person, one of the most common questions I get asked from people in this part of the world is ventilation's role on cooling and overheating. And the jury's still very much out on that, because ventilation here has typically been very much focused, a bit like the energy side of buildings, on keeping as much heat in the building as possible, being as energy efficient as possible, and providing good ventilation. But increasingly we're seeing technologies that have this kind of hybrid approach. So I'm thinking of kind of the Zender heat recovery, air conditioning type, where you have elements of cooling being brought in to supplement
free cooling potential.
So
I mean, a big thing again is that idea that we should, and that's that cooling ladder and that whole concept of we should be maximizing as much as we can the cooling potential available in the outdoor untreated ambient. And we should be then looking at our outdoor as a whole area of research, or a separate field, looking at outdoor comfort and outdoor urban spaces and how we design them. I think Matt Santamori made a comment, and I'm loosely paraphrasing, that, you know, heat should be should have an economic value and should be traded on a market in cities. You know, that if you're rejecting heat to the city, you should be paying a tax for that potentially. You know,
there was a company in the UK that had an amazing valve for heat recovery units that went up in the roof space. It was for houses that had solar panels, and it had four points on it from recollection. And basically what it would do is it would make a determination for the free heating or free cooling potential on different sides of the house and under the solar panel. So it would change where the supply air would come from, you know, and at virtually no cost. It would just literally a diverter valve go, I'm going to get heat from the solar side of the house or from the shaded side of the house. I'm going to get it from under the solar panel.
But it's amazing how
it's
amazing how rudimentary we can still be.
Yeah,
because a lot of it is mass rollout. A lot of it is it takes there's such an inertia sometimes in the building sector to adopt simple solutions in a way that are reliable and robust, I suppose, because no one wants to build something that's going to be tricky to maintain, because that's only going to cause problems for people and themselves. But
you've seen real benefit in this kind of cascade approach then, I take it, where it may not solve all of the problems all of the time, but it really stretches out the bandwidth of comfort for spaces.
Yeah, well, eliminate the need for cooling as much as you can. So design your measures, do your interventions, evaluate what cooling is available in your local climate before you resort to mechanical. So you might take 70-80% off the size of the mechanical air conditioning system. Maybe you still put one in, because there's a certain resilience in being able to extend the cooling capacity of a passive solution, you know, in extreme heat waves and short moments. So you might say, we don't have a large air conditioning system in our homes, but we may have some retrofitted solution that is already recognized that it needs to be 90% smaller than if you were to design it as the primary source.
Or you open up the opportunity to have systems that are capable of adding a little bit of conditioning to, say, a heat recovery unit, where where it doesn't have to do. It's not like you're conditioning the entire space. You're being intelligent about what you're doing passively, and then you're topping it up where necessary with conditioning.
Yeah. Like one thing that I think we should be looking at the feasibility of is reversible heat pumps. In Ireland, that we shouldn't be installing heat pumps that don't have a cooling option within them, because if you think about heat wave scenarios, and we think about this idea of redundancy, and if something is resilient, it can withstand unknown disturbances, from extreme events.
Is that practical now? Is that because I remember? I mean, we were talking earlier over coffee about the fact that I've come from a heat pump background in the day, and I remember people talking about heat pumps being used to cool underfloor heating and stuff 20 years ago, but it was always really difficult to actually do.
And that's what I'm saying. We should be active in that space, doing research on that. We should be looking for demonstration cases. This idea of demand response is a big thing now on the grid, and trying, like for me, I'm thinking, why can't we be running a heat pump for an hour at nighttime at temperatures that stay above the sort of dew point thresholds and risks you might have with that inside homes, but just to slowly cool down the structure at night.
And there's these blurring of lines as well, where it used to be ventilation and heat pumps and wet systems, and dry ventilation systems, but now increasingly we're seeing ventilation systems that incorporate heat recovery elements to them, both just like exhaust air heat pumps, but also even mechanical ventilation with the ability to both heat and cool air. So these devices are getting, a bit starting to build potential.
Having phase change materials within them that are accessing, they'll absorb heat, at different sort of temperature ranges, and they'll have their heat capacity is a variable, we'll say, subject to the environment they're exposed to and so on. It's just, for me, it's not a case of, all buildings just have to be able to withstand ambient warming through their structural design. Like, we can have mechanical solutions, but this idea of hybrid or mixed mode, accessing the free cooling potential, and then being a bit clever. If you're putting heat pumps in and you want to put 600,000 of these in, of course, we don't want 600,000 heat pumps running in cooling mode on the grid at the same time.
That's another problem.
That's another problem, right? But you may have a situation where you have vulnerable demographics. There may be some saying that is the backup. It's an emergency response only. And the UK have now developed a national heat resilience strategy. And I think Ireland need to be looking at that. Like, what is our national heat resilience strategy for the next 30 to 40 years?
That's interesting.
And looking at, there was lovely work done recently by Imperial College colleagues at Imperial College in London, where they looked at a mid-latitude city, and they said, if you put 50,000 exhaust or heat pumps into this city, what's going to happen to the heat, the thermal environment of the city at the city scale? Like, is this city going to end up with more of an urban heat island effect? Will it be a warmer city because we're rejecting heat now into the air from 50,000? I can't remember the number, but a significant amount of heat pumps. So there's all these interrelated stories. They put all these heat pumps in, they make us the ambient a bit warmer.
Do the only thing that makes me nervous about this is my experience in life so far has been, whenever we've mixed thermal comfort and air quality has always come out the poorer.
How do you mean?
Well, I've seen so many innovations over the years that have tried to recover heat from windows do something. Exhaust air heat pumps is the classic one where, hang on a minute, we can just take the heat out of the air and put it into the hot water. But now all of a sudden the focus is the amount of air that's being moved. The focus is on the energy aspect of it, not the air quality aspect.
Not the air quality aspect.
Yeah. And we've been very poor at that in the past. And we've got a poor track record with air quality and ventilation as it is, without muddying the waters about this balance.
Well, what's encouraging is SCI have their research development and demonstration fund, the RD&D fund. Yeah. And that funds a lot of research now. It's been hugely beneficial to the research community, the academic, but also industry, that we can pursue research, and we're getting a good, robust source of funding to pursue interesting ideas and things that can make a difference. And this year they had a topic that they wanted to fund, and it was looking more closely at ventilation under not just air quality, but air quality criteria, energy criteria, decarbonizing decarbonization criteria and cost criteria. Like, let's look more closely at our ventilation. What's the right approach to ventilate a home under all these criteria?
And the big thing driving that is the energy performance of building directives.
It is, yeah.
All of a sudden, I only just gone out this week on the podcast with Sten Renneboog from Eurovent, talking about the impact of the new energy, the recast of the energy performance of building directives.
It's going to make a big difference.
Made a huge difference because indoor environmental quality, which includes
first time front and centre. Okay, this is.
And this work that's happening is Ireland's example of a national body having to wrap its head around local implementation of the energy performance of building directives. And what they understand is that actually there's a new framing here where rather than just having minimum standards for ventilation, people can actually, they might want to determine outcomes that are more than the minimum. What do we even know what that means to us? What happens, at the moment we've always assumed that ventilation heat loss has been based around half an air change an hour in a residential setting. What happens if somebody wants an air change an hour? Have we got any way of actually knowing what that's going to mean at a national level?
A big problem, but
that's really interesting. And that RD&D funding you're talking about, that a lot of the
there's been some great work done, and with that, and that was just interesting to see that at a government level, that obviously was identified. That some of the ventilation, the NSAI ventilation validators have said that they think some of the systems are oversized, that they're too big. So there's an energy consequence, for that and so on. Some are saying they're undersized, that there's issues. And for me, it's all about this performance gap. The problem with buildings is we don't know what they're doing. No. Like, we talk all day long, we design all day long, but up until a few years ago, we had almost no data in Ireland on how our buildings are performing. And that's changed slowly. Construct Innovate and Jamie Goggins and the gang at University of Galway are collecting together data on many projects and trying to, let's say, make that available.
And that's interesting, isn't it, that the developers have rolled in behind that, the likes of Cairn Homes and others, that they've recognised that, well, actually, look, we've got to make some pretty nuanced and subtle decisions over the next 20, 30 years. It isn't just going to be what's the best U value for a product. We've got to think about embodied carbon, or we might be making, and without data, we're blind.
And even when you get the data, then that's just the observing the evidence. So you get the data and you say there is a performance gap. We've bit of work that we've just concluded. We presented recently where we show that the DEEP software, the DEEP compliance rating tool, which a lot of designers, at the domestic level, a lot of people would use it to influence their design. I want to have an A1 rated home. Well, we'll do some calculations. We'll use DEEP to influence that conversation. Whereas in non-residential projects and large scale, you have dynamic simulation tools and more advanced ways of let's say, predicting what will happen with buildings in advance. But we found that there was a 40% difference in the prediction. So DEEP was under predicting the amount of energy the home is using by 40%. And that performance gap is a big problem. Whether it's air quality, whether it's comfort, whether it's overheating risk, these sort of things. You can design buildings all day long, but until we start to get serious about large-scale data collection on how they perform, and almost like we talk a lot in one of our research projects about an NCT on heat pumps. We're putting in all these heat pumps and we know their performance can drift over time. Should there be an NCT on homes, or should there be some accountability to say this building was built and with 2 years later, it's already underperforming massively?
And back to my favourite analogies of cars. I think the interesting thing is when we start getting down to a component level of data, you start to have the ability to A and B profile different components within the same buildings. Actually, which one is giving us the best outcomes? You don't get that with that, but that's been happening in the automobile industry for decades. They know down to fine art which fuel pump is giving them the best longevity and best performance, because they've been A and B profiling them for years.
They have,
right?
But their data set is so huge. Again,
but this asset is what, 30, 40, 50, 60, 80 grand tops, for the vast majority of cars. It's a tiny value.
You're paying $500,000 and upwards now for
homes. Yeah. And yet you're working almost...
You spend 80% of your time there.
And you're spending you've got almost no data. Yeah. But if you had component level data coming out of those buildings, the quality of building that we would have at this stage. Because not only do you improve the visibility for the consumer, you also improve the visibility for the entire supply chain, all the way back to the original manufacturer. And now all of a sudden, as a manufacturer of, say, a ventilation fan, your reputation will live and die by the real long-term operational performance.
And then the problem with that is, like all things, the amount of external factors influencing how a building performs are so many that there's no one, let's say, stakeholder accountable. So there's always, so the fan might underperform, but it might be how it's actually being used in a behavioral sense by the occupant. It might not be the technology itself. So it's a very protracted problem, and it's down to, again, it's not necessarily an overheating and ventilation example. It's just one that comes to mind, is that we've been looking at this heat pump database, and we're doing a bit of work on them. And it's the people who are on this database, they sign up themselves. So they're conscientious users. They're interested in their own system performance. And we see that those systems are performing better than other ones we've monitored in social housing, and where you don't have a conscientious consumer or someone who's interested. So you're right, like the problem isn't those people. Some people are really interested in their buildings running well. The challenge is for all those people that aren't, but they're yet being exposed to poor conditions, as a result of that.
Yeah, that's really interesting.
It's just trying to figure that out a little bit, trying to understand that there's a huge behavioural challenge with thermal comfort, but also in buildings that don't have any ability to intervene mechanically. It's a behavioural problem then.
Yeah.
Educating those people then having the motivation to adjust their environments and respond. And then you're into that area again where you've got the demographic that actually can't intervene. Elderly people, infants, neurodivergent.
We've got to build spaces for everybody. Yeah, we build buildings for people.
Yeah,
that's always it. Always comes back to that ultimately, doesn't it?
It is. And there's a lot of physics and science needed to get that to work well consistently at a large scale,
Very exciting. I mean, I'm full of hope and excitement for the young kids coming into the built environment world at the moment, because it's a really exciting space. Like when you think of the opportunities you've got, scientific, engineering wise, social science, behavior, like
the data, like analytics alone, because we are slowly getting there. That we have companies now, and they specialize almost entirely in their offering is around data. We'll install sensors and we'll manage that data for you, or we'll intervene in your systems depending on AI-driven algorithms that are looking at data and so on. There are huge, exciting opportunities, smart buildings, smart readiness, but you've got to kind of get away from that sort of the fashionable sense of these words and the kind of buzz terminology around them, and get into, well, what does that really mean? Like, how do we genuinely make them smart? And a lot of buildings, it's just, it is about the occupant, it's about the human,
who is it did a talk recently on are we smart enough for smart buildings yet? It was a really good talk. You do it's a good segue onto what you do here, because there's quite a broad remit of certainly as a research group, you're looking across thermal comfort, heat pumps, a whole range of it. Tell me a little bit about the work you're doing here in a minute.
Yeah, we are doing a few different bits. As a group, there's other actually aspects of the group that I'm not involved in. So I'll speak to my own, but we other colleagues who are involved in agri-engineering, and anything that's an energy system that you can intervene, simulate, optimize, we kind of would be involved in. But
so the key is energy systems, like
for that group, it's kind of energy as the underpinning, and like I work in buildings. Another colleague would work in renewable systems, offshore wind and so on. Another colleague would work in agri-engineering, and then they'd have sort of groups, under them and so on. But like a lot of work we do is around indoor environment, for a long time. Ventilative cooling actually was a big thing that, we've been involved in here, is looking at the cooling potential of ventilation technologies, which is a little bit of a misnomer for someone living in Ireland, because you'd say, why waste time on cooling? I mean, that's not the immediate need locally. But research isn't local. Scientific findings have applications far beyond your own region and so on. And we worked on the International Energy Agency EPC project, Annex 62, ventilative cooling, back 2015, 2016, 2017. And it was out of that then that we became very interested in this idea of ventilative cooling, because it turned out that, again, the science was there. Sometimes the physics can be there, but it hasn't been translated into regulatory tools, design tools, policy that's clear to understand. So you're trying to take this messy research and say, let's formalize this a little bit. Let's try to develop some frameworks. How you design for ventilative cooling? How can you design to maximize that outdoor potential in the air, that cooling potential?
And for people that aren't familiar with the EBC, that is the the remit of the EBC is to create from research practical knowledge that can be used by national governments to implement. So ventilative cooling was a very good example of that. There's a lot of academic stuff going on, but how do we translate that through that annex, through the AIVC, actually something that people can use as tools on the ground?
Yeah, I think there are great opportunities to engage with, because you get to work with experts around the world. You come together, you bring your research to the table, and you kind of distill that then into a couple of useful outputs, whether they're reports, tools, whatever that might be. So it was through that we became interested in this idea that there was a need for cooling in buildings that would traditionally not have been seen to need cooling. So like cool climates, because of how we're designing our buildings and so on. So a lot of our work has been around that area. We've done quite a bit actually on the aerodynamic performance of windows. So a lot of window designers, we design our windows. The thermal performance is hugely significant. What the U value is, what the psi values of the frame is, the thermal bridging. Then you're looking also at the daylight, performance and the solar gain performance. But it's rare enough that you'd get a conversation or that there's a regulation exists to say that. We do have regulations that will say you should achieve a certain amount of air changes per hour inside in a space, or you should try and achieve a certain flow rate. But there's not as much research gets done on, or at least there's not much, we'll say, applied knowledge available on aerodynamic performance. So when you open a window, what happens?
So you're getting into, this is where you start to see regulations of 1/20th of the floor area on a 30-degree window or whatever. What does that actually mean?
What does it even mean? And it's like, and they have come from, this idea of that percentage of open area to floor area is a good metric to just help regulatory bodies say, let's just work with a number that has been informed by research. But we here have looked a lot at louvers. You see now more and more architects are moving towards louvered solutions as the airflow pathway into buildings. So, and we did a building here back in 2012. I think it was, I'm going to take a punt and say it was Ireland's first commercial NZ retrofit in 2011, 2012. We refurbished part of the building and we monitored that then. We refurbished part of a building here and we monitored then for a number of years. And within that, we had a combination of automated and manual openings. So the occupants could intervene with their own ventilation, but we had CO2 driven and temperature driven overrides as well. So you had this kind of mix of automated and manual. And some of our work has looked at how we used a louvered solution. So what was the aerodynamic performance of those? How many louvers should you have? What angle should they be at? Are they actually counter productive for airflow rates or not? Do they perform better under wind-driven airflow exchange or buoyancy-driven airflow exchange? Because you have these very different sort of local environments. So a lot of our research is sort of chamber. We've done some laboratory work on those. We've done some field work. And we found actually with a guide vane solution, so if you could think of a window that actually opens, it pivots at the center, we'll say, to create a kind of a guide vane when it's open, that you could increase the air change rate by a factor of 5 compared to a plain opening.
If the wind is coming at a facade, if depending on the angle it's coming at the facade, you can catch it better.
And you just don't see enough of this. Some of our computation fluid dynamics research using large eddy simulations showed that you've got an upwash flow, a downwash flow, or a transversal flow along a facade for larger buildings, depending on the wind direction, right? And then in reality, you should be trying to exploit that it's not just the same flow at all times, it changes depending on conditions. So if you have openings that will actually respond to that, like that can really improve the amount of air you can push through buildings, which is a comfort problem more than an air quality problem, because I think the amount of air you need for good air quality would be lower than the amount of air you need to remove heat.
That's really interesting. And is that technically being done anywhere?
Yeah, I mean, again, it's back to examples. It's all, like I've seen designs, they've won I've seen a couple of buildings recently that won the RIBA Sterling Award, schools in the UK, fantastic looking facades. And I went digging, I couldn't find any measured evidence. It would be great if we were better at making data available, monitoring and publishing, because the big challenge for these, and it comes back to our earlier conversation, is it's very easy to commission an air conditioning system as a contractor. You can come in, you can actually You can validate the flow rates in the ductwork, you can validate the air supply in the room, and you can say it's going to run like that consistently. It's a constant air supply system. You build a new building that relies on openable windows to cool that building. Very hard to commission that because it'll be different every moment of the day and every...
I have this conversation with natural ventilation the whole time. You know, like it's not that natural ventilation doesn't theoretically work. It's the fact that it's very difficult on a given day to come in and know if it's working or not. That's the difficulty.
And I'd love to develop some solution there and say, like we've got low cost mobile solutions we've made for research where we can go into a room and we can set up very quick and do a CO2 spatial sort of distribution study, and we can kind of, using CO2 as a proxy, we can kind of infer ventilation rates. But you're right, like it's a difficult thing that you'd have to go back multiple times, build some sort of report. And I think that's another, that is why it has some bad press, you know, that it's not really commissioned and there's not enough post-occupancy investment in making them work, you know.
So you did some work with the European Union technical specification. That's one of the things you've been doing recently, yeah?
So I think before... And I'm not someone, sometimes I get a bit lost in the quagmire of standards. I'm not a standards guy. Yeah. So there's a complicated, let's say, architecture around how standards are developed and made and where they sit in the overall framework of their own particular standards, family of standards. But I was involved in a new technical specification, which I think is below a standard. You write a technical specification first with SEN. Then that becomes, then you do some more work.
Yeah, that's the TSEN before it becomes
the TSEN. So we've just finished the TSEN, and that's going to be published, I think, in January, as far as I know. But I'd have to check that, but early next year. And that's, it's called designing for ventilative cooling in buildings. So it's a standard now and that's where that cooling ladder is with the cascade ethos and so on. It's in that standard.
And did some of that learning come out of the EBC work ultimately?
Oh, absolutely. It was the same gang. It was the people from Annex 62. Yeah. It was led by Yannick Roth and Christopher Plesner at Windowmaster and Velux. They were participated with us on Annex 62. There was a compelling evidence came out of 62 to say we really should be working towards standards on ventilative cooling, largely because some of the EPBD family of standards don't properly account for the contribution you get from VC in your rating calculation, if that makes sense. So we're doing energy performance calculations in Europe, and the argument was that, well, the amount of cooling we're getting from natural ventilation isn't actually being properly accounted for. And the new RED2 directive has now, for the first time, said that any air supply above that needed for hygienic purposes that makes a contribution to cooling can be counted as a renewable energy. Yeah. Which is fascinating. We're now
and I think that works a really good example of how industry and academia cooperate on this stuff as well. Yeah. That we often see that there's this friction between industry and research or standards because there's this fear, obviously, of lobbying and
of course.
And at the end of the day, Velux and Windowmaster make windows, and it would make some sense that they're involved in understanding their contribution to cooling in buildings, right? But these people are like the Christopher Pelsners of the world, are like brilliant technical people that can really add value to those discussions.
Without them, standards, without them, the writing wouldn't happen. You need them to drive it. As academics, we're constantly pulled in many directions, and it's great to come together. I thoroughly enjoyed working on that writing group. And to work with industry, and they're pushing in one way, you're pushing in a different way, and there's a good dialogue there. And out of that can become a practical standard that's useful, because you can publish a lot of research studies, and they can be very interesting to contribute to knowledge and advance knowledge in a research way, but they may not be directly translatable into something that's useful for practitioners. So that's
and I remember I was chatting to Bart Kramers from Zender, and he was saying that the interesting thing that industry brings is often they're innovating at the coalface really fast and hard as well, so that they're learning stuff in parallel and sometimes even ahead of academia. They go, well, actually, hang on a minute, we've got that tech. That's already going in, and we're collecting data on that. So, if you don't have those relationships with industry, you miss all of that.
Absolutely, yeah. And actually, we've just worked with Bart as well, monitoring one of his systems with him. So going in and doing that performance thing and saying, this is a really nice tech. It looks like it works well. Bart had some data, and we said, let's work together on that.
And that brings some independence and rigor.
Yeah. And we looked at it and said, you are right. Like, the performance is in fact as we hoped it would be. And then just coming back to that technical specification, the idea of that is that it's a guide to assist designers. We've developed this 9-step process. So it's a feasibility stage process, because you can avoid most of the vulnerability in buildings if you intervene early in the design. The earlier you intervene in a design, the more likely you are to capture good ventilative cooling potential, because actually a lot of the decisions are architectural. It's not ductwork driven with air-cooled chillers that you can come in later and say, put the chillers there, here's your service riser, get the cooling into us. It's actually orientation, where are you in terms of altitude? It's looking at kind of, the facade is hugely important. So getting in early and influencing those decisions was very important. So the technical specification focused almost exclusively on a feasibility stage design process to assist designers in good VC.
Good truism for life, that, I think.
You get intervening early. Was it? A job well begun is a job half done. So getting in early and starting well means you're halfway there. So we focus on that, and actually it was Anna Maria Belleri at URAC Research in Italy. She led the kernel of that work. She developed a ventilative cooling potential method, which took some European standards around how you calculate the thermal performance of buildings, and she adapted those to evaluate for a given climate and building combo. Basically, can you meet your cooling needs using natural ventilation? If you can't, well, maybe you need supplementary, but that calculation process didn't really exist. And now it's here in a technical specification that the argument is countries can adopt this into the regulations easier. So that I think is interesting work. It's exciting. And
talking of interesting work, one of the things that really caught my eye that you've been doing is this kind of research on schools as potential climate shelters. We've been talking about overheating. That's a really interesting idea. Tell me about that.
And that kind of comes out of, we didn't participate actively on Annex 80, but we monitored, or we were aware of their work, and they've developed this idea of, up until recently, we knew what structural resilience was because we had earthquakes. We had to deal with this, we knew what, fires and things like that. So we had, resilience was very much a structural thing. But now we recognize that we also need thermal resilience in our buildings. They should be resilient to thermal shocks that are unknown now, and they may, unknown events, we'll say, in the future. So this idea of thermal resilience came out of a lot of work that Annex 80 did. And again, we had this study. We are actually publishing the report in the next sort of 6 weeks or so. It was funded by the SEAI in Ireland, and we looked at the resilience of non-residential buildings in Ireland, and that involved healthcare, offices, and schools. And we were trying to, basically evaluate, is there overheating? Are they actually resilient to ambient warming, but also their own internal conditions? And in that work, we drifted in a little bit to this idea of climate shelters, because I think in California now and in other parts of the world, there are regulations obligating people to have a cool bunker in their home, that you should have one room that has some capacity to be conditioned or to be maintained at a certain temperature, so that if there is an extreme heat wave, you can withdraw to that space. It's a safe space.
Yeah, right? Makes sense, yeah.
And we were looking at it then with the schools, saying you have large classrooms, they're not occupied in July and August typically, and they're always at the center of communities that have vulnerable elderly people, young people and so on, that they might not actually have resilient homes. Could they be used as heatwave climate shelters, that people would go there for a number of days if we were having major, heat waves and so on? So, and again, with a bit of hybrid, adapting the system slightly to having some mechanical ventilation, not mechanical cooling, but having some fans installed, you could actually cool enough overnight to say, yes, this can work well as a climate shelter, so communities could make use of the school.
Interesting, yeah.
And just part of a heat wave plan, like something that I think is needed is heat wave, whether at national level or just even at a local council level, starting to look at heat wave planning. What do we do if we do experience a severe heat wave? Do we have solutions that can, deal with certain demographics again?
The other thing that I think is really interesting is this idea of kind of the double jeopardy planning as well, where, you know, we've just been through a pandemic, for example. So one of the things they're having to figure out in North America is, well, what happens if you've got a pandemic and a wildfire at the same time, right? Which is a very plausible scenario in a lot of circumstances. What if you've got power outages and a heat wave? Right? There's these. It's not just necessarily one problem or another.
Or I'll give you another situation
because heat waves do generate power outages.
And actually, a major barrier to the uptake of ventilative cooling is air quality, urban air quality. So if you have high pollution, you can't open your windows. If you can't open your windows, you can't cool the apartment. If you can't cool the apartment, you now have a high risk situation. So you have that propagating effect. So it's those multifaceted scenarios where we need some work done on when we expect to see high contaminant or pollutant urban events. What's the effect of those on our capacity to cool? Are they chronic or short term? You know, and looking at that. And actually, we've done some work. We looked at 10 schools in Cork City, and we looked at the urban air quality in proximity to those schools in collaboration with our colleagues here in MESO Research at MTU. And we found that actually nitrous oxide and PM2.5 were very high to the point that about 74% of the time, I think it was over 12 months, you couldn't, if you were to actually take account of that as a barrier, that you wouldn't actually ventilatively cool the space with that air quality outside. So just, and that we need to do more work on that and see where that goes and look at it a bit more closely. But it was showing us that there are certain outdoor contaminants that would restrict you being able to do some cooling. So that's about back to how resilient is your cooling system?
And it shows that's what I quite like about the work of ASHRAE's 241 is this idea of modes of operation for buildings, that there are normal modes of operation in non-overheating scenarios, in normal operation, and it kind of goes back to what we were talking about at the beginning. But there are scenarios where that building needs to switch up a gear for some reason and be able to take account of a pandemic, an overheating scenario, wildfire, smoke.
And it may not be at the building scale. Like that's, I think that the solutions need to be looked at. You've got the room scale, you've got the building scale, but then you've got the urban scale. You know, there's different scales that you can come up with solutions. And that was that climate shelter narrative we were saying. You can solve overheating risk or heat stress in those homes by having a school nearby that you can be into within.
And it's this idea of spaces as safe havens, that you know, there's all sorts of reasons why that space might be the best space you can be in today. I mean, there are it's one of the best advocacies I've heard for better air quality in schools, is that a school classroom might be the only place a child gets to go where they're thermally comfortable for 8 hours, where they've got access to decent air quality, in the same way that it might be the only place where they get a square meal, right? There's all sorts of social reasons why these spaces might offer up the only respite some people that are more vulnerable get being in a decent space.
And it's why we need more than just engineers and architects involved in these. You do need people who have a better awareness of socioeconomic background and factors, as you say, psychological factors, and that there's a more sympathetic approach that's inclusive.
Do you find the social sciences and things come into your work quite increasingly now?
Yeah, not enough. And that's because we just probably need to get better at pursuing grants and support to allow us to do that better maybe. But certainly more and more you're building in those facets now to your work. That part of this work was we will engage. I mean, again, we have this project at the moment that's looking at the performance gap. So Project Reduce, it's called, and it's looking at how to reduce the performance gap in the difference between asset rating tools and what we see in practice. But one of the work packages there is the role of the occupant. So UCD are leading a piece of work there for us on that project, and they'll be looking explicitly at surveying people who are in homes where we have a big performance gap. And why is there a performance gap? When do you use your heat pump? Why do you use your heat pump in that way? Like, why do you use your windows in that way? Why do you turn the hot water on then? So what's your perception of your energy systems? What are the factors of you as a person that influence how you use your energy in your building? And how can we try and address that at the design stage, at the compliance stage?
I think that's where it really gets really interesting when you start involving the citizen science side of this stuff as well. Like, are we even asking the right questions as scientists often? That bringing in people into that space.
And we definitely need to get better at trying to unlock the citizen science approach, that how can we actually better access the population to help us with these questions, because we find it very hard when it comes to buildings. It's an intractable problem to get access to a building, get access to occupants who will participate in surveys, collect both the observational, objective data from the building, get the subjective occupant data, and get that at a sufficiently large scale that it's statistically significant that you can draw conclusions that help us make decisions. It's a big problem, the sample size,
Yeah, and as Sarah, I can't remember her name now, I'm so sorry, Sarah, who is involved in citizen science. She's with us, the Stockholm Institute, and they do a lot of citizen science. One of the things she was saying about citizen science is you only get so many runs at people when it comes to studies. You run out of capacity. There's only so much.
There's a fatigue. There's like a survey fatigue thing kicks in.
Yeah. So if you're including citizens in the science, inevitably they're designing the research around stuff that's of benefit to them as well.
Yeah.
So you'll get a longer run with people if there's something of value to them. If all we're interested in engineers is how long a pump's going to last and what the PA pressure of X, Y, like you're going to lose people in the room really, really quickly. But actually that may not be what they want. Other people may want to know other things. Is we're opening my windows for half an hour in the morning of benefit to my air quality?
That example we had of that home where you had 4,000 ppm for 6 hours at a typical night, like consistently over the year. In their bedrooms, they had 4,500 ppm in the room. They don't know that yet, but when we go back to them and talk to them about that might lead to some an informed decision to change that behavior somehow, Yeah. So it is, you're saying you got to try and show people the evidence, maybe build in a bit of, what's the word, not to motivate them, but they have some agency all of a sudden now and they've got some skin in the game to some extent. Yeah. And then trying to marry that with low cost tech that you can, so sensors that are cheap but reliable. So there's a big role there for the ICT people to be able to say, we can produce, sensors and instrumentation that will sample at a good enough rate. We'll give you research grade, reliable results or data that you can trust, and then being able to just roll that out, we say, on a wide scale as well. It's just a big challenge. I mean, it's just very hard to get large scale data, I think, for buildings. And I think we need it. Until we get it, that performance gap will always be there. And as long as that's there, we're reporting out in a way that's, it's misleading. We're kind of saying we're achieving X in our emissions or our homes perform a certain way. And we're seeing that in reality it's very different,
Paul, it's been absolutely brilliant talking to you this morning. Thanks so much for your time. It's been a pleasure. And I knew it was going to be fascinating, and we ended up down some all sorts of interesting rabbit holes.
Lots of digressions there, diversions. Yeah. No, delighted to talk. Yeah, delighted to be here. Super job.
Brilliant. Thanks a million.
Thanks, Simon.
Thanks for listening. Before you go, can I ask a favour? Before you shoot off to whatever it is you have to do next, or even the next podcast, if you enjoyed what we've been talking about here, please do spread the word and let's keep building this community. And don't forget to check out our sponsors in the show notes: Ultra Protect, Eurovent, Erico, ACO, Farmwood and Zender, all amazing companies, and without them this podcast would just simply not be possible. Check them out in the show notes at airqualitymatters.net, and do check out our YouTube channel. All this content is there, plus much more. See you again next week.